Section 3.5, expectation. In this section, we're going to be talking about the concept of expectation, or sometimes we call it expected value. And what we mean by that is the long run average value. The long run average value. In other words, expectation is not what's going to happen if I do something once, but rather what's going to happen on average if I do something many, many times. There's a formula we're going to use to figure out expectation. And the formula is first outcome times probability of the first outcome plus second outcome times probability of the second outcome. Most of the time in our problems, there will be two outcomes, and we will use this formula. However, sometimes we must extend the formula to more than two outcomes. Sometimes there might be three or four or five or, more than two. But most of the time, there's two outcomes. For example, success or failure, or win, lose, or live, die. First example says, Jake flips a coin with his friend every day. If it comes up heads, Jake wins, and his friend gives Jake $1. If it comes up tails, Jake loses, and Jake has to give $1 to his friend. What is Jake's expectation? So let's go through this problem. Here's the formula. Whenever you're doing an expectation problem, the formula is first outcome times probability of first outcome plus second outcome times probability of second outcome. So what's the first outcome? The first outcome, or one of the outcomes, is that Jake could win, that it could come up heads and Jake could win $1. And the outcome, what we mean by the outcome is the monetary outcome. And so first outcome is that Jake could win $1. And you multiply that monetary outcome by the probability of that happening. The probability of him winning $1, the probability of the coin coming up heads. So if Jake flips a coin, you need to think, what's the probability that it's going to land on heads? Of course, we know that is 1/2. That's what we mean by first outcome times probability of the first outcome. There's a 1 out of 2 chance that it's going to land on heads. So what we're calling the first outcome in this problem is that the coin lands on heads. That means the second outcome is that the coin lands on tails, which means Jake loses the bet. The second outcome is that it lands on tails. Jake loses $1 because he has to give $1 to his friend. And so what we do in that case is negative $1. So we put the money is positive when it's coming into Jake's pocket, it's negative when it's going out. And then we multiply that by the probability of that happening. So what's the probability when you flip a coin that it lands on tails is what you should be thinking. Of course, that's also 1/2. There's a 1 out of 2 chance that the coin flip would land on tails. And then you go compute this on your calculator. Of course, you don't put in the $sign, but actually, would hope you wouldn't need a calculator for this one, to be honest. I would hope you can see that the answer is 0. But if you do go put this in your calculator, it's going to be 1/2 plus -1/2, which of course is 0, and we're talking money here. So Jake's expectation is $0. Let's talk about what that means. What does it mean for his expectation to be $0? Because he can never, I mean, that means basically break even, right? He can never break even on any single coin flip or any single day, because each day that he does this, he's going to either win $1 or lose $1. So he will never break even on a single day. That's not what expectation means. Expectation is not talking about what happens on a single day or a single time that we do this. Expectation is talking about what happens if we do this hundreds of times in a row or thousands of times in a row, even millions of times in a row. And so what we're saying is when we say his expectation is $0, we are saying that it's as if he played this game thousands of times in a row. It would be as if he broke even every day. Again, of course, he won't break even any given day. He will win some, he will lose some. But what we're seeing is he'll probably win about half the time, and he'll probably lose about half the time. When he wins $1. When he loses $1. In the long run, he will probably kind of just break even. That's what this is saying. In the long run, the net gain to Jake will probably be about $0. So he's not going to get rich playing this game. He's not going to lose a lot of money playing this game. In fact, probability says nothing's going to happen at all to him if he plays this game in the long run, because he's going to win some money, lose some money, but most likely pretty much break even. Okay, let's move on to the next example. That was a pretty easy example, kind of a warm-up problem here. But that's the basic way that these problems go. That's the basic formula. Jake stops by the local gas station every day and plays a game with the employees. From a shuffled deck, Jake picks a random card. If Jake picks a face card, he wins $364. If he does not pick a face card, he loses and has to pay $104. What is Jake's expectation? So now the stakes are higher. Last problem, it was just $1 we were talking about. Now Jake could win a lot of money, right? He could win $364 if he picks a face card. And Jake could lose a decent amount of money also. He could lose $104 if he doesn't pick a face card. Now you might say, this seems like a great game for Jake because when he wins a lot more than when he loses. He only has to pay, you know, $100 when he loses, but he wins 300 something dollars when he wins. It seems like maybe this is a good game for Jake. And maybe it is. Maybe the probabilities are in Jake's favor. It's possible they are, but we have to be very careful because yes, Jake wins a lot of money when he wins, but he only wins if he picks a face card, and that's not going to happen very often. There's not that many face cards in the deck. So he's not going to win as often as he loses. He's definitely going to lose this game more often, right? There's a lot more cards in the deck that are not face cards. So we got to be very careful. I'm not sure how this one's going to turn out. As far as the expectation is are things going to be in Jake's favor with this game, or is the deck stacked against him? The formula is expectation equals first outcome times probability of first outcome plus second outcome times probability of second outcome. The first outcome could be, or you can call it whatever you want. But basically, I'm going to say, let's have the first outcome be that Jake wins. He wins the bet. It does turn out to be a face card that he picks. And we'll call the second outcome that he loses the bet, meaning when he picks that random card out of the deck, he does not pick a face card. So the first outcome, money-wise, is that he would win $364. It seems great at first, but it's not going to happen very often. There's not a ton of face cards in the deck. In fact, let's remind ourselves about what a deck of cards looks like. And we will see out of the 52 cards in the deck, there's only 12 of them that are face cards. Just as a reminder, it's these 12 over here on the far right. When we say face cards, we mean the ones with faces on them. And those are the jacks and the queens and the kings. So there are 12 of those. In other words, there's a 12 out of 52 chance. There's 52 cards total, 12 of them are face cards. There's a 12 out of 52 chance that Jake will pick a face card. So that's what we mean by probability of first outcome. The probability that Jake is going to win the $364 is 12 out of 52. In other words, if Jake were to play this game 52 times in a row, we would expect that he'd probably win about 12 of those games. Is it for sure that he will win 12? If he plays 52 times in a row, is it for sure that he will win 12 times? No. That's just what probability says is most likely to happen. It's very possible that Jake could play this game 52 times in a row and maybe he only wins 5 of the times. Maybe Jake plays this game 52 times in a row and he wins 20 times. Both, there's a lot of things that are possible. But what we're saying when we say 12 out of 52 is we're saying that's the most likely thing to happen. If that's what we would guess would happen, that's the thing that has the highest percentage chance of happening. That's what probability says is the most likely thing to happen, is that he would win 12 out of 52 times. And that means he would lose the other times, right? So the second outcome is if he does not pick a face card, he loses the game and Jake has to pay $104. Paying money means that's money coming out of Jake's pocket. That's negative money as far as Jake is concerned. What's the probability that he's going to lose? Well, if 12 of the 52 cards are face cards, that means the other 40 are not. If these 12 on the far right are face cards, then the other 40 on the far left are not face cards. You could just do 52 minus 12. That's another way to get 40. So we believe if Jake plays this game, there's a 40 out of 52 chance he's going to lose. Or another way to say that, if he played this game 52 times in a row, we believe he would most likely lose 40 of them. He would most likely win 12 times out of 52 and lose 40 times out of 52. That's what we're saying here. Then you got to go put that in your calculator and see what you get. Remember, your final answer is going to be money, but you don't need to put dollar signs in your calculator. When you do put this in your calculator, I suggest putting it in all at once if possible. In other words, I suggest just putting it in this whole line in at the same time if you can. If you don't have a calculator that seems to have the ability to do that, some people end up just doing this part first and then doing this part and then adding the two answers together, for example. That's okay. You have to be very careful. If you're going to do it that way, you have to be very careful that you do not round off. I don't know that that's an issue in this problem, but that definitely will be an issue in some of our problems. In other words, if you're going to do it that way in general, if you're just going to multiply this first and try to get that answer, and then multiply this and get that answer, and then add afterwards, do not round off at all. In other words, write down everything your calculator says here, and then add, and then you will get the same answer that everybody else is getting. Again, though, if you can, I would suggest putting it in all at once, this whole thing, and getting an answer right away, because then we're not rounding off in the middle of the problem. Sometimes we still have to round off at the end of the problem, but you don't want to round off in the middle of the problem and then again at the end of the problem, because then your answer may not look the same as everybody else's. If you do put this all in your calculator, I believe the answer is $4. And it's a positive $4. Since this is positive, that actually means this is a good game for Jake. That actually means if Jake plays this game in the long run, he's likely to win some money. That's what that means. Since the fact that that expectation is positive means Jake is likely to win some money if he plays this game a lot. I'm not suggesting that you go start playing this game with your friends if you could talk them into it, but if you played this game every single day for the next, hundreds or thousands of days, it would be as if you won $4 each day. Of course, you can never win $4 on any particular day. Every time you play this, you are either going to win $364 or you are going to lose $104. You will never win $4 on any given day. But that's not what expectation is talking about. Expectation is not talking about what's going to happen if you do this once. It's not what it's talking about. Remember, the definition for expectation was the long run average value. What we're saying is if we played this game over and over and over, hundreds or thousands or even millions of times in a row, it would average out to be as if we won $4 every day we played. Yes, you're going to win some. Yes, you're going to lose some. In fact, you're going to lose a lot of the days. You're going to lose most of the days, right? You're going to lose 40 out of 52 days. But when you win big, right? Even though you only win 12 out of 52 times, you win big compared to what you're losing. And so it actually averages out in Jake's favor. If Jake could talk the gas station employees into playing this game every day, he's probably going to come out ahead in the long run. Again, I'm not suggesting that Jake goes and does this because he could lose $104 several days in a row to start off, and then he's not doing well. But expectation is not talking about what happens if you play this once or twice or 10 times. It's talking about what happens if you play this a lot of times. So I'm always think like, what happens if you did this thousands of times in a row? That's kind of how I like to think of it. How would things average out? Well, if Jake played this game, thousands of times in a row over a period of many years, it would average out as if he won $4 every day. That's what we're talking about. Jake likes to play a game at the local Sky River Casino. He rolls 2 dice. If it comes up totaling at least 7, Jake wins $20. Otherwise, he loses and has to pay $30. What is Jake's expectation? So now Jake, every day after class, maybe on his way home, he stops by the casino. There's a game they have there where, very simple, you roll two dice. If you get at least seven, the total of the two dice is at least seven, you win 20 bucks. If not, you got to pay 30 bucks. What is Jake's expectation? So, first outcome, second outcome. I mean, one of the outcomes is that Jake wins money, and one of the outcomes is that he loses money, right? I don't care which one you call first or second, but let's just say win, lose. He wins when they total at least seven. He loses if they don't, otherwise. First outcome is that when he wins $20. By the way, this would be a very good time for you to pause this video and try this problem. We've done a couple expectation problems now. This is the third one. I think you probably could do this or at least attempt to do this. So I suggest you pause this video and try to finish this problem and then come back and see how you did. Okay, so the first outcome is that he could win $20. We have to multiply that by the probability of that happening. The second outcome is that he might lose $30, negative 30. And then we have to multiply that by the probability of that happening, right? So let's go find those probabilities. Let's go talk about the probabilities of Jake winning versus Jake losing. Remember, Jake wins if the total on the dice comes up at least seven. Jake wins if the total comes up at least seven. That means seven or more. That's what we mean by at least seven. At least seven means it could be seven and he wins, or it could be more than seven and he also wins. So let's go remind ourselves what it looks like when we roll two dice. So here's a nice chart we've used in the past about rolling two dice. You can see there are 36 outcomes. We need to go count how many of those outcomes add up to at least seven. That means seven or more. Well, the ones on this main diagonal, starting at the very bottom left, going up to the very top right, those are the ones that add up to exactly seven. And then all the ones down and to the right of that add up to more than seven. So what we need to do is go count all of these from that main diagonal, bottom left, all the way up to top right, and then all the ones down and below to the right of it. We have to count all of those because that's how many of the 36 are adding up to at least seven. So there's 1, 2, 3, 4, 5, 6 in this row, or in this diagonal, I should say. So 6 plus 1, 2, 3, 4, 5 right here, plus 1, 2, 3, 4, plus 1, 2, 3, plus 1, 2, plus 1. So basically, you need to go 6 plus 5 plus 4 plus 3 plus 2 plus 1. So go ahead and do 6 plus 5 plus 4 plus 3 plus 2 plus 1. I think when you do that, you get 21. In other words, I think there's a 21 out of 36 chance that Jake's going to win. If he goes and plays this game, there's a 21 out of 36 chance that he's going to win. What are the chances he's going to lose? Well, remember, he loses if they don't come up to at least 7. Otherwise, that just means if that doesn't happen, he loses, right? I don't know that we need to go look at the chart again. I mean, I think if he wins 21 out of the 36 times, you should be able to figure out how often he loses out of 36. Basically 36 minus 21. If you go 36 minus 21, you should see that that's 15. I mean, I think it's logical for me to say if he wins 21 out of 36 times, he's going to lose 15 out of 36 times. If you don't like that, if you're like, I'm not sure, this guy seems a little shady, I don't believe him, I want to go check for myself, well, go ahead and go to the chart and then find all the ones that don't total to at least 7. That means they total to less than 7. You would see, here's one that adds up to 6. 1, 2, 3, 4, 5 of them that add up to 6. So 5 plus 4, these 4 add up to less than 7, plus 3, these 3 add up to less than 7, plus 2, plus 1. Again, there's 6 of these. So 6 plus, let me try that again. Might have misspoken here. There's 5 of these. There's not 6 of these. There's 5 of these that add up to the number 6. I got to say that properly. There's 5 instances where it adds up to 6. So 1, 2, 3, 4, 5. So go ahead and do 5 plus 4 plus 3 plus 2 plus 1. So 5 plus 4 plus 3 plus 2 plus 1. That would get you to 15. And that's why we have a 15 there. That's a different way of thinking about it. So you might say, great, this is great for Jake. Go for it. You're going to win more than you lose, right? You're going to win 21 out of 36 times, and you're going to only lose 15 out of 36 times. Of course, Jake should play this game. He's going to get rich, right? Because he wins more often than he loses. Well, yes, he wins more often than he loses, but when he loses more money than when he wins. So we're not sure how this is all going to average out until we actually go compute this. Not sure what's going to happen until we actually go compute this. And if I go put this in my calculator, and again, I'm trying, if you can, you should try to put it in all at once. And what I mean by all at once is all in one line, like compute it all at the same time. So now I want to press enter, right? Like it looks like that. Now I want to press equals and see what happens. And so I'm probably going to have to round off because that's a big, long, ugly decimal answer. Negative 0.833333333, you know. It's okay to round off at the end, but you don't want to round off in the middle of the problem. In other words, like if your calculator is such that you think you need to do this first and then do that and then add those 2 answers, that's fine. Just don't round those off. Keep your whole long ugly decimal here, keep your whole long ugly decimal here, and then add, and then you will be getting the same answers that we're getting. Because you don't want to round off both in the middle of the problem and then again at the end of the problem. Your answer just gets more off. And we are talking money here. I'm going to put approximately because we are about to round off. The answer is negative. We are talking money. And since we're talking money, I think it's best to go to the pennies place because we don't have money past the pennies place. You can't give someone a portion of a penny. And so if you round to the nearest penny, it's 83 cents. But it's negative 83 cents, which is a big deal. It's a big deal because that means this is not a good game for Jake to play in the long run. The probabilities are not in his favor because this is a negative number. What we're saying is If Jake were to play this game over and over and over, if he stopped by the casino every single day for years and years in a row, it would be as if it would average out to be as if he lost 83 cents every day. Even though there is no particular day where he will lose 83 cents, on any given day, he will always either win $20 or he will lose $30. But that's not what expectation means. It doesn't mean what will happen on a single day. It means what's the long run average value. What will happen if Jake plays this over and over and over, thousands of times in a row? And what we're saying is he's going to lose money in the long run. In fact, it's probably going to average out to be as if he lost 83 cents every day. So this is not a good game for Jake to play. But people do stuff like this all the time. People go to casinos all the time and play. And I guarantee you, every single game at the casino, you have a negative expectation. When you're going in to play that game at the casino, your expectation is negative. In the long run, you're probably going to lose money. You might win a bunch of money on a single day. In the long run, if you played every single day, years and years in a row, it doesn't even matter what you're playing. You most likely are going to come out behind. And that's because the casino, they took statistics. Somebody who works at the casino took statistics and they know how this works. They know the expectation formula. They're not going to offer a game where the player has a positive expectation because that means the casino would be offering a game where they know they lose money in the long run. How are they going to stay in business? Nobody would run a business where they know they lose money in the long run. So the casino only offers games where they know they're going to win money in the long run. In other words, they know the player has a negative expectation. If you, like Jake, have a problem, you can call 1-800-GAMBLER or you can text 800 GAM. Chat 1-800-GAMBLER chat.org. Next couple of problems we're going to talk about have to do with insurance. In insurance, when we use the word premium, we mean that to be the amount you pay for an insurance policy. It's the amount you pay to purchase the insurance policy. That's what the word premium means. Then there's a person we're gonna talk about for a minute called an actuary. Actuary is a person who compiles and analyzes statistics and uses them to calculate risks and insurance premiums. So there's a person who decides the premiums. There's a person who figures out how much you have to pay. And that's because when you get insurance, there's a lot of things going on, right? Any type of insurance that you get. If you get car insurance, it's not like everybody pays the same amount on car insurance. The actuary goes and figures out how much you're going to pay because they figure out what's the probability that you're going to have to be paid out on. What's the probability you're going to get in a car accident? If you're a teenage boy, you might pay more in insurance. If you've already been in a bunch of car accidents, You might pay more in insurance than somebody who hasn't. If you're a 40-year-old woman who's never gotten a ticket and never been in an accident, you may not have to pay as much insurance as somebody else who's been in 3 accidents and got 5 tickets and 2 DUIs. Right. So the person, the actuary figures out, how much people have to pay based off of the probability that the insurance companies, the likelihood that they're gonna have to pay out on you. And so I just talked about car insurance for a minute, but what we're going to be talking about for the next couple problems is life insurance. By the way, if you really like statistics and you want to make a lot of money, this is one of the top jobs as a statistics major. This is one of the top jobs as far as making money. You can make a lot of money as an actuary, as a statistics major. What we're going to talk about in this section or in this last couple problems is life insurance. There's 2 types of life insurance. There's term life insurance and there's whole life insurance. Term life insurance is cheaper, but it just goes for just like a term, maybe like a year for 5 years or maybe 10 years. But term life insurance is like stops after a certain term is over. Whole life insurance goes your whole life. It's more expensive. It's a little more, it's definitely more expensive than term. But the benefit of this is that it lasts for your whole life. So no matter when you die, the insurance company is going to pay out on the life insurance and your family gets a lot of money, a decent amount of money. This is different because say you only get a 1-year term life insurance, your family only gets paid out the money if you die within that 1 year. If you don't die within that 1 year, it's over. It's done. If you die, if you get a 1-year term life insurance and you survive the year and then you die, after 2 years, you don't get any money because your term is up, right? And so that's the difference. In this next couple problems, we are going to be talking about this one. We're not going to be talking about whole life insurance. However, my advice to you, if you can afford either one, you should get this one. You should get whole life insurance if you can. But I know not everybody can because sometimes it's more, costs too much. And so some people go with this. Okay. By the way, I did want to share a screen with you here. So this is a actuarial life table, and this is used by the United States government, Social Security Division of the United States government. And it's a table that actuaries created that basically tells you the probability that somebody's going to die within the next year. It splits it up by male and female. Male, female. I'm only showing you this because I'm showing you like this is the type of work that actuaries might do. They might go through all the numbers and put together these types of things. And then life insurance companies could use these types of things. For example, so again, this is male on the left, female on the right. They're usually fairly close, but females are usually projected to live a little bit longer. And so that's why they split it up, males and females. For example, if you took a random I mean, you see, these are very like these are all like practically zero until you get up to even you turn it into a percentage by moving the decimal point, 2 times to the right, it's still 0 point something percent. So, for example, if you're a 40-year-old male, if I move that decimal to the right, it's still 0 point something percent. There's a 0.37% chance that you will die within the next year if you're a 40-year-old man. So what this is the probability. This here represents the probability that a 40-year-old female will die within the next year. This over here is the probability that a 40-year-old female, sorry, I might have said that wrong. This is for a male right here. This is for a female, right? So this is for a 40-year-old male, the probability they will die within the next year. This is for a 40-year-old female. This is the probability they will die within a year. But both of these are very, very small. You see how they're 0 point something, right? But what I'm saying is even if I move the decimal over twice to the right to turn it into a percent, it's still 0.2% here, or 0.3%. I have to go down to 56, I guess, until it's not 0% anymore, or 0 point something. This is the first time it's 1 point something, right? So a 56-year-old male, if you move this decimal twice to the right, there's just over a 1% chance that a 56-year-old male will die within the next year. But even that's very small, right? That means there's a 99% chance they're good, right? Um, Say, for example, uh, grandpa's turning 68. They're having a birthday party for grandpa this weekend. Grandpa's turning 68. You want to go to your grandpa's birthday party. You like grandpa, but you have this big party that your friends are having and you want to go to that too. You could always pull up this actuarial life table and go look, okay, he's turning 68. If I move the decimal twice, that's 2.3, a little over 2%. Um, there's only a 2% chance grandpa's going to die in the next year. Maybe I skip this birthday party. There's like a 98% chance he's going to have another one. I'll go to the next one, right? Maybe I skip this party and go to my friend's party. I don't know. I'm not telling you that's what you should do, but this actuarial life table could help you make decisions like that. What if grandpa's turning 119 and they're having a birthday party for grandpa that weekend? I don't care how big this party is that your friends are having. You better go to grandpa's birthday party. There's a 90% chance it's going to be his last one. It's about a 90% chance grandpa's not going to make it to be 120. There's a 90% chance that he's going to die within the next year. You should go to grandpa's party. So again, you can use this table to make life decisions such as those. But tables like that are where we get problems like this, or it's where we get the probabilities like this. Insurance companies use tables like that to determine what they're going to charge you for a life insurance policy. Probability that a 25-year-old male will die within 1 year is that very low, right? It's almost zero, but it's not exactly zero, but it's very close to zero. Suppose the premium for a 1 year, $60,000 term life insurance policy for a 25-year-old male is $150. What is the insurance company's expectation for this policy? Okay, in other words, the 25-year-old male walks into the insurance company, into the office, and said, I want to buy a 1-year, $60,000 term life insurance policy. And the insurance company says, great, that will be $150. What that means is the 25-year-old male pays $150 to the company. And if the 25-year-old male dies within the next year, the insurance company will pay out $60,000 to the family of the person. Let me say that again. The $150 represents what the person pays to buy the policy. That's called the premium. And then the $60,000 represents what the insurance company will have to pay out if the person dies within the year. Okay, the insurance company, they don't want you to die. They're rooting for you. They're like, come on, live, live, live at least a year, because then we don't have to pay anything, right? The families, the people who make a lot of money if the person dies, but I'm not saying they're rooting for that, but the insurance company doesn't want you to die. They want you to live because then they don't have to pay any money. In fact, if the person lives through the year, the insurance company just made $150, right? And so when we talk about first outcome, second outcome in this problem, it's really first outcome is live, or one of the outcomes is live, the other one's die. It doesn't really matter what order we do these in, but live and die are the two outcomes, right? The person's either going to live throughout the whole year or they're going to die at some point during that next year. As far as the insurance company is concerned, again, we are doing an expectation problem, but we are doing this from the point of view of the insurance company. We are not doing, they are not asking us to do this from the point of view of the 25-year-old male. We are doing this from the point of view of the insurance company. In other words, we own the insurance company. We want to figure out what is our expectation. We are the insurance agent. We want to figure out what is our expectation. Okay, so it's very important whose point of view we're doing this from. We are doing this from the point of view of the insurance company. So we actually run the business, we're selling the policy, we're trying to determine if we're going to make money on these policies in the long run. The first outcome is that the person could live and we just made $150. Right? That's pretty straightforward. Second outcome is that the person could die, and then we're going to lose a bunch of money. Right? So it's positive money. We make $150 if the person lives throughout the year. We lose a bunch of money if the person dies during the year. Okay? What is the probability that the person's going to live throughout the year? We weren't directly told that, but we were told the probability that the person's going to die within the year, right? And so you should remember the rule of complements. Living and dying are opposite events, right? And so the rule of complements that we have learned in the past says that if you know one of the probabilities, you can subtract that from one, and then you will have the other that you're looking for. In other words, if this is the probability the person's going to die within the year, I can subtract that number from one to get the probability that they will still be alive a year later. And so what I think we should do for right here is 1 minus 0.001507. um, 0.998493. I mean, there's over a 99% chance. That's almost 100%, but there's over a 99% chance that the person's going to survive the year. I mean, they're a 25-year-old male. Of course, It's a very high chance they're going to survive the year. So what that means is more than 99% of the time, the insurance company simply makes $150 off this deal. That's almost 100% of the time, right? But it doesn't happen all the time because some of the time the person died. This tiny probability here, but this is the probability the person dies. This is what I need to put over here, of course, right? This is the probability that the person's going to die within the year. And I left this for last because a lot of people put the wrong thing here. This is if the person does die, how much money does the insurance company lose? And a lot of people want to put 60,000, like negative 60,000. Right? Of course, it's going to be negative because they lose money, but a lot of people want to put negative 60,000. And I understand why, because it says 60,000 right there, and that's the payout. That's what the insurance company has to pay out to the family. So I understand why some people want to put negative 60,000 there. It's not the right answer though. And the reason is because they're not actually out $60,000. If the person does die, they're not actually under, the insurance company is not actually under by 60,000 because we have to remember when this whole thing started, they were already up by $150. The person had to pay $150 just to buy the policy. So they're not out the entire 60,000 because they started up $150. So in other words, what I'm saying is what we need to do to get this part is $150 minus $60,000. It's going to be close to negative 60,000, but I'm just saying it's not exactly negative 60,000. It's actually negative 59,850. So be careful about that. I would say that's one of the things that I think like a common mistake type of thing in a problem like this. Um, don't put negative 60,000 there. It's close to that, but they were up a little bit when the person gave them money to buy the policy. Okay, go put all this in your calculator. Again, as I said earlier, try to put it in all at once so you're not rounding off in the middle of the problem. If you can't, you just have to do this part first and then do this part second and then add. That's okay. But write down everything your calculator says here, everything your calculator says here. In other words, don't round off and then add those two answers. And then you might need to round off at the end. Maybe. Sometimes you do, sometimes you don't. I'm not saying every time you're going to have to round off. This is not always an issue, but sometimes it is. So if you do put all this in your calculator, I'm going to go ahead and do it also. It's 150 times 0.998493 plus negative 59,850 times 0.001507. Actually, this one turned out nice. I did not seem to need to round off at the end. It looks like $59.58 is what I got. So I don't need to put an approximate sign because I'm not rounding off. But I would, if I did need to, I would round off to the nearest penny. So what we're saying is if we are the insurance company, notice that's a positive answer. We're saying if we are the insurance company, this is a good policy for us to sell because we will make money off it in the long run. If we sold one policy like this every day for the next many, many years, it would be as if we made $59.58 every single time we did it. That's what we're saying. Because yes, there will be times that we lose a lot of money. It's a lot of money that the insurance company loses when the person dies and they have to pay out. But that just doesn't happen very often. It's so low of a probability. That's almost zero. Not quite. That's almost zero. So most of the time, over 99% of the time, we're just going to simply make $150. Person hands us $150. We say, thank you. We just made $150. That happens almost 100% of the time, but not exactly 99.8% of the time. And so what we're saying is it averages out. Yes, they win money a lot. They lose money occasionally. It averages out to be as if the insurance company just makes this much money every time they sell it. That's the long run average value. That's what expectation means. For the last problem, I have one more problem. This is a tough one. I'm actually going to kind of go back and forth because we're going to need this one while we're doing this one. So I might kind of switch the pages back and forth. Alexis works as an actuary for State Farm Insurance. A 105-year-old male comes in wanting to purchase a 1-year, $35,000 term life insurance policy. The probability that a 105-year-old male will die within the next year is 0.444309. That's pretty high. Help Alexis figure out how much to charge for the premium in order for State Farm to have a positive expectation for the policy. So in this problem, we don't know the expectation. We're going to figure out what does the expectation need to be. I'm sorry, I said that wrong. In this problem, we don't know the premium. We're trying to figure out what does the premium need to be in order for the expectation to be a positive number. Because we want the if we are the insurance company, we don't want to be selling policies where we have a negative expectation. For the insurance company and we're selling policies, we need them to have a positive expectation for us because we need to make money in the long run. We're running a business. Insurance company would never sell a policy where the insurance company has a negative expectation because it would never, a business should never be doing something where they know they're going to lose money off of it in the long run. So let's do the same thing as far as like live, die. If the person lives, the insurance company makes some money. We're not sure how much money though. It's whatever the premium is. I'm going to call that X for now. Since we don't know what it is, let's call it X. So just kind of put something to the side. I don't know what the premium is. We're going to try to figure that out. I'm going to call it X amount of dollars. What is the probability that the insurance company is just going to make whatever that premium is? Well, it's the probability the person's going to live. So this is very similar. Remember how we had to do 1 minus this for the last problem to go here? That's the same thing we're going to do. We need to do 1 minus point. Let me actually squeeze that up here. 1 minus 0.444309 is what we need to stick right there. Okay, so go ahead and do that. 1 minus 0.444309, 0.555691. Okay, so again, what are we looking at? This is the amount of money the insurance company will make. This is a positive number here because that's what the person paid in the premium. But we don't know what it is yet. We're trying to figure it out. So we're just calling the premium X for the moment because we don't know what it's going to be. But whatever that X amount of dollars is, that's how much money the insurance makes. And there's just over a 55% chance that's going to happen. This is the probability the person will live throughout the year. Remember, this is the probability the person will die within that next year. So this is the probability that person will live throughout the year. And then over here, we have what's going to happen if the person dies. The insurance company is going to lose some money. And then what's the probability the person's going to die and the insurance company loses money? Well, I already know this part. It's right there, right? probability the person's going to die within the next year is given to us as 0.444309. That's the probability the person will die within the next year. If the person dies within the next year, the insurance company is going to lose some money. How much money do they lose? Let's be careful what we put here. Remember, the insurance company has to pay out $35,000, but that doesn't necessarily mean I'm going to put negative 35,000. Remember what we saw on the last problem is the insurance company was going to have to pay out 60,000, but that didn't mean I put negative 60,000 there. We took the premium minus the payout. Let me write that down because this is important. Premium minus payout is what ends up going here. Premium minus payout. And premium minus payout. So that's what needs to go in that spot right there for our problem that we're looking at right now. Right in that spot needs to be premium minus payout, just like it was in the last problem. The premium, we don't know, it's X. The payout is 35,000. Premium minus payout. And no, this is a lot, and this is not an easy problem, but that's the expectation using X as our premium. And what do we need this to be? We need this to be a positive answer. We're trying to make this a positive answer. Positive means greater than 0. What positive means. We now can't have a formula. Actually, we have an inequality that we're trying to solve now. This whole thing needs to be greater than 0. What does X need to be for this whole thing right here to be greater than 0? We need to go solve this inequality. Positive means bigger than 0. All right, so let's go through the math to solve this inequality. When I multiply X by a number, it's simply the number next to X. Like we write this in algebra as 0.555691X. Okay. For this next part, I actually have to distribute in sort of like a backwards distribution. So this 0.44 number is going to multiply to the X, but it's also going to multiply to the negative 35,000. So when I sort of reverse distribute here, it's going to be 0.444309X. And then when I sort of reverse distribute here, it's going to be minus whatever that times 35,000 is. So go ahead and do 0.444309 times 35,000. I'm getting 15,550.815. And we want that to be greater than 0. Let's keep going with the math here. These are like terms. We can add those other like terms because they both involve X. Go ahead and add up the coefficients. Add up the 0.55 number with the 0.44 number and see what you get. And when you do that, you actually get 1. It actually combines to 1x. You shouldn't be surprised about that though, because remember how we got the 0.55 number is we took 1 minus the 0.44 number. So of course those two numbers should add up to 1. That's how we got this number in the first place. So it shouldn't really surprise you that those two numbers add up to 1. So I have 1x minus 15,550.815. We want to make sure that's positive. I could add the 15,000 number to both sides, right? If I add it to the left side, it disappears. If I add it to the right side, it's over there. And so I have 1x greater than the 15,000 number. I don't really need the 1 in front of the x, by the way. So if we add the 15,000 number, it goes over there as a positive. add it to both sides. And this implies 1x anyways. If you don't put a coefficient in front of your variable, it implies, we assume it's 1. So we're kind of finished. Like, we need to make sure that our premium, remember x is our premium, we need to make sure that our premium is greater than this amount of money. In order for the insurance company to have a positive expectation, we need to make sure the premium is more than that. What do we mean by more than that? This is just over 81 cents, right? So bump it up to the next, I would bump it up to 82 cents. I would say something like this. Let's see where I can squeeze this answer in. I would say for my final answer, premium needs to be more than that, which is $15,550 more than that would be bumping that up to 82. It needs to be that much. The premium needs to be that much for the insurance company to have a positive expectation. Of course, it could be more, and that would be great. The insurance company just makes more money the bigger it is. But that's like the minimum premium we could be talking if the insurance company is hoping to make money off this deal. This is the minimum amount they should be charging for the premium. They should be charging that much or more. Okay? Because that's the first answer that's bigger than 81 cents is 82 cents. You say that's a lot of money. $15,000 for a 1-year term life insurance? That's a lot. Well, of course it is. I'm talking about a 105-year-old. If you're a 105-year-old expecting to get life insurance, you're going to pay a lot of money because there's a very high probability that the insurance company is going to have to pay out on you. So the older you are, the more you're going to have to pay on your life insurance if you're talking about term life insurances. Um, the younger you are, the less. And that's all because of the probabilities and the statistics and what the actuaries figure out and the probability they think they're going to have to pay out on you. All right, that is the end. Thank you for watching.